Hi everyone, this is Yaowei Han from Kyoto team. Today I will introduce our system description for voice privacy challenge based on voice-indistinguishability. And then today's content will contain 5 aspects. The first one is voice-indistinguishability. It's a voice print privacy proposed previously in our work. Then the second one is about voice print perturbation mechanism. That means how to design a mechanism achieving our voice print privacy. Then third one is privacy preserving speech synthesis framework. And the first one is privacy guaranteeing. Here I will introduce our privacy guaranteeing of released speech dataset. And at last, I will introduce our results for voice privacy challenge and also compare it with our baseline 1 and the baseline 2. So for voice-indistinguishability, I will introduce how to formally define voice print privacy. So let's first see definition of metric privacy. If we have two secrets, S1 and S2, then after perturbation, the metric privacy will guarantee that the outputs will have difference at most the product of distance between S1 and S2 dot epsilon. So we can see it has several advantages. The first one is it has no assumptions on the attacker's background knowledge, but just limited knowledge the attacker can obtain. The knowledge is about the difference between secret 1 and secret 2. The second advantage is privacy loss here can be quantified. Because we have a factor epsilon, then the bigger epsilon, the more knowledge about the difference between S1 and the S2 can be known. Thus, the better utility, the weaker privacy. And also, we have a distance. So here, if we can properly choose the secrets and the distance metric between secrets, we can apply the metric privacy for anything. But when applying metric privacy, deciding secrets and the distance metric for voice print is not so trivial. Firstly, what's a secret? We know it's voice print, but how to represent the voice print? It has several choices, and among those, we choose S vector, a widely used speaker space vector. For example, it's a 712-dimensional X vector. But how about the metric? That means how to define the distance metric between voice print. How about the Euclidean distance? But it cannot well represent the distance between two X vectors. But how about constant distance? It's widely used in speaker recognition, but unfortunately, it doesn't satisfy triangle inequality. That means it's not a metric, but it's very important in our metric privacy. Finally, we find angular distance. It's also a kind of constant distance, but satisfies triangle inequality. So here, I paste our voice-indistinguishability for single user and also for multiple users in a speech dataset. First, let's say for single user, our voice-indistinguishability guarantees that if we have two X vector at X and X prime, then the difference between the possibility of outputting tilde X is smaller than e to the epsilon dot distance between x and the x vector. Here, the distance is their angular distance. So here we can say epsilon is our privacy budget, also privacy utility trade-off. So the bigger epsilon, the weaker privacy but better utility. Then for multiple users in a speech dataset, we propose speech data release under voice-indistinguishability. So if we have two data sets, D and D prime, and they have only one different X vector, which are x and x prime. Then the difference between the possibility of outputting tilde d is smaller than e to the product of epsilon dot distance between d and d prime. Here, the distance between d and d prime equals to the distance between dx and x prime. Here we have another factor n. It means speech database size. And here we can see the larger n means the stronger privacy. And this has been proved in our previous work. Then after we have voice-indistinguishability, how to design a mechanism achieving our privacy definition, we borrow the idea from differential privacy. We use the exponential mechanism. So if we have a x0, then the possibility of outputting the x tilde will be proportional to the e to the minus epsilon dot the distance between x0 and tilde x. So here I gave a table. Here we can directly see how it perturbs the x vector. But where do x0 and x1 to the x3 come from? Here we need a x vector database. So if we have a speech database, for example, maybe laboral speech, then for each speaker with numerous utterances, we will use the mean of x vectors extracted from these utterances. That means, firstly, we will extract all of these x vectors, then compute the mean of x vectors extracted from these utterances from the same user. Then, how to implement frameworks for private speech data release? For a raw utterance, we will extract its f-bank and x vector. Then, after perturbing the x vector, we will use the synthesized model and waveform vocoder to get a protected utterance. That's the privacy preserving speech synthesis framework. Here, the x vector is protected, and so that we get a protected utterance. So the first one is privacy guaranteeing of the released private speech database. If we have a sensitive speech database, here the speaker A has record 1, speaker B has record 2, and speaker C has record 3. Then after applying our method, only the voice print is changed. That means the x vector is changed, but our content will be same. So after perturbation, we will get an anonymized speech database. Here, speaker A will have record 1 but with 6 voice print. Speaker B has record 2 with 8 voice print and X total. That's our privacy guarantee. Then at last, I will introduce our results. For ASV results, I paste the part of results and only about laboral speech. So we can see compared with baseline 1, the speaker verifiability results are a little bit worse than only the trivial utterances are anonymized. But we have better results for meeting the first requirement. That means when both the trivial utterances and the in-row utterances are anonymized, we can still identify certain user. Then after compared with baseline 2, we have overall better performance. For ASR results, we can see compared with baseline 1 and baseline 2, for VCTK dataset, we have similar, even better performance. But for laboral speech dataset, we don't perform very well. There is an easy explanation because our X vector database are constructed using the sensitive database itself, so that the distance between the original X vector and the numerous possible transferred X vectors in the laboral speech dataset are so big that it influences the final WER results. And that's all. Thank you.